Today, we are going to continue with the feed-forward controller because yesterday we have not yet completed that feed-forward control. Yesterday, we have seen feed-forward controller. The purpose of feed-forward controller is to reject a particular disturbance. The disturbance that can be measured can be rejected by using a controller called feed-forward controller. The problem with the feed-forward controller is it will not reject all disturbances. It will reject the only disturbance for which it is designed. But on the other hand, feedback controller reject all disturbances, including unknown disturbances. Whatever may be the disturbance, if it deviates the process variable, the feedback controller will reject. But it is not so with the feed-forward controller. It will reject the disturbance for which it is designed. Therefore, we have to design the feed-forward controller that often occur. In other words, that gives a large deviation. Because of the disturbance, if we get large deviations, then we must design a feed-forward controller. Second thing is, we cannot use feed-forward controller alone. Already the reason we know, because feedback controller reject all disturbances. On the other hand, this will reject only the disturbance for which it is designed. Therefore, we cannot implement servo. It cannot use as a servo controller. That's why we cannot use feed-forward controller alone. It should be used along with feedback controller. That is one of the reasons. Another reason is feed-forward controller is not a closed loop stable system. It is like almost open loop system. That's why there is no guarantee that the system will be stable for that feed-forward controller. That is another reason. Therefore, all feed-forward controllers has to be used along with feedback controllers. So it is a very good tool to reject the disturbance for which it is designed. Here, two feed-forward controllers are designed. One for the feed flow rate. If any change in feed flow rate, definitely it will affect the temperature inside the heat exchanger. That's why we have to monitor any disturbances entering by through this flow rate. So a flow transmitter is there. Disturbance rejection is designed for flow rate. And if any change in inlet temperature of the feed that is entering into the process, then also there will be a deviation in the controlled variable. That's why another controller is designed, feed-forward controller. Both what it will do, both have the same manipulated variable that regulates this valve. That regulates this valve. Therefore, but here the feedback controller is not mentioned. The heat exchanger, the stream is entering into the jacket that transfer its heat to the process fluid. If this block diagram represents only feed-forward controller, that's all. Another example, distillation column in which both reflux ratio control as well as reboiler, both we have a feed-forward controller. The reflux ratio is based on inlet temperature of the feed. Feed is entering here into the distillation process. If inlet temperature changes, definitely there will be a change in temperature inside this distillation column. That's why we can reduce the temperature here if we inject more reflux ratio. Reflux ratio, particularly to improve the quality, but here it can reject this disturbance entering through this feed-forward controller. Anyhow, this disturbance definitely will reduce the quality of the product. So That is one way. Another way is this reboiler. Reboiler means here already we have seen that the bottom product is a liquid in the distillation column. The entire temperature is maintained by injecting heat into that liquid. The liquid will be pumped out through this, again pumped through the circulated. It's not, we should say like that. It is circulated through this process, through this heat exchanger. The heat exchanger will supply steam here. That's why heat will be transferred to that bottom liquid. This is here, if any change in composition of the feed, for that this reboiler is designed here, that will regulate this the steam that transfer its heat to the process fluid. The third example is CSTR. In that, next one is we are going to see how to design a feed-forward controller. First, let us consider this this CSTR. In that, heat is applied here, and the inlet flow rate is F5. Inlet temperature is Ti. Outlet flow rate is F. The process temperature is T. That's why the outflow rate also have the same temperature of T. Then here the two disturbances that considered here are the Ti, the inlet temperature, and the flow rate of the feed. Both are considered here. You know that what is the mathematical model of level process? Here it consists of both level, it can be modeled as both level as well as thermal process. If you consider it as a level process, you will get A dH by dt equal to total inflow rate minus total outflow rate. That is equal to amount of mass accumulated inside. If you write for changes, you will get the equation for changes. Then it will be linear, and we are not going to see those things. That and all you know. So it is the mathematical model for level process for changes. Similarly, this is the mathematical model of the thermal process. Thermal process. On the left hand side, this is amount of heat accumulated inside the thermal process. This is amount of heat entering. If you multiply this by rho Cp, then only. If you multiply this part, and Q is actually a heat energy quantity. That's why no need to multiply by rho Cp. If you multiply this and this by rho Cp, this is the amount of heat amount of heat accumulated inside that CSTR. And this is, if you multiply this by rho Cp, this is amount of heat supplied by the feed. And this is the amount of heat, if you have Fi T rho Cp is amount of heat removed from the CSTR plus heat supplied. So that's all. But we want to design a feed-forward controller for a change in inlet temperature. We want to design a feed-forward controller for change in inlet temperature. Now, you consider again this. Let us assume that there is no deviation in there is no accumulation of heat, there is no deviation. Dt by dt is 0, there is no deviation. At steady state, this part must be 0. Therefore, if you write the equation for steady state, right hand side equal to 0, from that we can write T equal to, you are dividing both by Fi. So you will get T equal to Ti plus Q by Fi rho Cp. So we got one expression for T. What is our aim? Our aim is, therefore Q equal to Q equal to Fi rho Cp multiplied by Ti minus Tp. So if you bring this, you can manipulate from this equation like this. Q. So this is the controller. This is the controller at steady state. The amount of heat required to keep this T equal to set point. That's why this T is replaced by T set point. What we will do? Suppose we are having any controller, we will give the set point. And the set point given is TCP. Set point given is TCP, and the controller will do necessary controller will do necessary correction so that the process will be at T degree centigrade. So this is fed back here like this. So what is our aim? We want to make T equal to set point. So what is the design objective here? We want to make T equal to T set point. This is the idea behind the any controller. We want to make output equal to the cross variable. PV must be equal to set point. That is the idea behind any controller. PV must be equal to set point, in which the T must be equal to set point. That this T must be equal to set point. That's why replace this T by T set point, and we are going to supply heat to the process. How much heat has to be supplied? That is the manipulated variable. This much amount of heat is required to make T equal to T set point. That is the meaning of this feed forward controller. The meaning of this feed forward controller, if you find Q by replacing T by T set point, this much amount of heat is required to make T equal to T set point. Therefore, Fi rho Cp multiplied by T set point minus T. So now we can design that controller. What is first thing what we want? T set point minus T is required. What is T? The what is T here? Sorry, Ti, not T. Ti. We are designing a controller for inlet temperature. What is inlet temperature? A temperature transmitter gives that to the controller. That is subtracted from T set point. That is subtracted from T set point. This one I will explain later. Now you forget about this one. T set point we are supplying, and TA is applied. The difference we got here, we get T set point minus, here we are getting T set point minus Ti we are getting. So if we have to multiply with rho Cp Fi. So let us assume that Fi is constant. We are maintaining for this disturbance. Otherwise, we have to measure this Fi and we have to supply here. That's not. We are assuming that Fi is constant. For constant feed flow rate, if temperature changes, this controller works. So Fi rho Cp is mentioned here. That is multiplied by T set point minus T. T set point minus T multiplied by Fi rho Cp. That is the amount of heat required to maintain T equal to T set point for this disturbance. That is very important. So it regulates the valve steam flow rate is regulated so that the heat supplied will maintain T equal to T set point. That is the idea. This is called a static feed forward controller. In other words, here what we made, if you include this dt by dt, that is dynamic element, rate of change of temperature with respect to time, dynamic element. If we are making that there is no changes in T, that is T is at steady state, for that we are designing a disturbance. That's why we are making this equal to 0, and we took the steady state equation and designed here. That's why static, steady state means static. So this is a static feed forward controller we designed. But this is not true during dynamics. If any disturbance is entered, suppose this is a step change means this part is dynamics. It changes from 0 to 1. So because of the sudden change, it will not, this will not work. It only works for steady state values. This controller is for steady state. That's why the dynamics given by this controller may not be acceptable. That's why um, we have to modify the design, the dynamic feedforward controller. That's why we have to consider a dynamic equation to design this feedforward controller. So here, if you again you consider the same equation, V by Fi, dt by Fi here multiplied by Fi. No, you brought that Fi here. Another thing is this is simplified equation of thermal process. We didn't notice. We didn't. The aim of this class is not to derive this mathematical model of thermal process. That's why take it as granted. You can refer to the book Stephanopoulos, Chemical Process Control by Stephanopoulos, if you want to know the mathematical model of this. So our aim is for a given mathematical model, how to design the feed-forward controller. That is our aim. That's why we didn't see how to obtain the mathematical model on that. Now you can bring this, divide the entire equation by Fi. It can be written like this. You can write the equation like this. In that we want to take Laplace transform on both sides, because this equation is for changes. That's why we can take Laplace transform on both sides. That gives this. So this is nothing but V by Fi S plus 1. If you assume V by Fi as tau, if you assume this is equal to tau, if you assume this is equal to tau, then you can write this part equal to tau S plus 1. This is not t, tau t of S. We can write, if you take Laplace transform, you'll get this. Here I wrote t dash of S. So so it means it is for changes, but let us assume t. T of S, if you divide on both sides by tau S plus 1, you will get the equation. So T of S equal to T I of S by tau S plus 1 plus 1 by Fi rho Cp, all are constant. We are assuming that constant feed flow rate, 1 by tau S plus 1 Q dash Q of S. So here again, if you want to find if you want to find the controller, means we have to find the Q equal to what? Again, you bring keep this Q one side and bring all to the right hand side. You will get tau S plus 1 T set point of S minus Ti of S. So here you will get, instead of in the static model, the difference between the static model and this is this part. Take Laplace transform. We are not making this equal to 0. We are assuming that the dynamics part is there, because we are designing a dynamic controller. So what we are getting is tau S plus 1 as the additional term that should be multiplied by T set point of S. That is the only difference. So if you therefore the amount of heat required equal to Fi rho Cp, we are assuming that constant feed flow rate tau S plus 1 multiplied by set point of S minus inlet feed temperature. That's all. So here, if you come here, dynamic, here earlier we have seen that here one, that is static feed forward controller. Here the dynamic it becomes tau s plus 1. Tau s plus 1. So if you multiply the set point, if you multiply this set point by tau s plus 1, that is a filter, here, that should, through that the set point should enter here, then it is a dynamic controller. Dynamic, all other things are same. So inlet temperature is measured, compared with the set point multiplied by that filter, and it is given to f by rho Cp, so it regulates the value. So same. The only difference is, instead of one, some filter is here. That is the only difference between the two. Another thing is, this is not physically realizable. You can simulate, but this is not physically realizable. If tau s in the numerator, it's difficult to realize. All physical system will have, already we have seen this, all physical systems will have at least first order. No system in the world is zero order, at least first order. So that's why it is not a practical controller. Theoretically we can talk like that. You know that okay. Anyhow, if you simulate that, how to obtain practical, that and all we'll see later. Here, this is the load rejection by load rejection by static, and static, and this is dynamic feed forward controller. This is static feed forward controller for servo response. Response is set point change, set point step change. You notice that um, T is changed here. A step change is introduced in T. For that, how dynamic controller works, how static controller works. If you see that, definitely the dynamic controller gives better response. Now let us design one more. Let us generalize the design of feed forward controller. Here we consider we designed from the mathematical model of CSTR. For that we designed. So these are all fundamental equations from the first principle. We use those equations here, these two equations, to design the controller. Instead, we can generalize the procedure. Now let us generalize the procedure. To generalize the procedure, first we have to write this from the block diagram. What is y of s? Y of s is the process variable, that is equal to the m of s manipulated variable given to the process. So we can write y of s. If this part is not there, we can write gp of s multiplied by m of s. If disturbance is coming there, then it must be through gd of s. Gd of s, gd of s, disturbance model, through that d of s is coming. Both are added together, you will get y of s. That's written here. So y of s equal to gp of s, m of s, gd of s, d of s. That's all. Then already I said we have to design the feed forward controller by assuming our aim is to make y of s equal to y set point of s. That is our aim. The purpose of designing this controller is making y equal to y set point of s. That's why substitute y of s equal to y set point of s to design the controller. Now find m of s, because m of s is the manipulated variable. That's why if you bring all to one side except m of s, then you will get this equation. This is the controller controller for the disturbance d, whatever may be the disturbance, but it must be measurable disturbance. Measurable disturbance. If it is a measurable disturbance, For that we can design, because it is on the right hand side. That's why it must be measurable. If we are having a measurable disturbance, then we can design a controller, a feed-forward controller that will reject reject the. So the feed-forward controller is M of S. M of S equal to um, 1 upon GDS, y set point of S. Why set point of S? Because our aim of the controller design is we want to make y equal to y set point. Some assumption we have to made while designing the controller. That's all. So we made an assumption that we want to make y equal to y set point. That's why we are substituting y equal to y set point. So we got this equation, that is 1 upon GD of S. This is the disturbance model multiplied by y set point of S minus D of S disturbance multiplied by GD of S, disturbance model, divided by GP of S. So here this 1 by GD of S must be multiplied by y set point of S. Then it should be subtracted from D of S. Therefore, main feed-forward controller is this GD of S by GP of S. But the set point must be multiplied by 1 by GD of S, because from general we can understand that this is y set point means what should be the output, what is the expected output. Y set point is expected output. We cannot compare this expected output and disturbance. It is obvious. That's why this block. So we can think the other way, that this expected output is converted into converted in terms of disturbance, That way also we can look this controller. That's why in a feed-forward controller, the set point will not be directly subtracted from the measured disturbances. Then it will go through some filter, because we want to convert the set point into a variable that relates DFS. That is that way also we can look this controller. So what is the final controller? The set point must be multiplied by 1 by GD of S. That is G set point. So set point is given here, that is multiplied by 1 by GDFs, that is available here. That is subtracted from this measurable disturbance. Here you will get 1 by GDFs y set point. Here what you are getting is 1 by GD disturbance model multiplied by y set point minus D of S you are getting, minus D of S you are getting. That should be multiplied by, see in the previous here it should be multiplied GDS GP of S. Already we have seen that what is GD, what is GP. Already we have seen that. Once again we will see what is GD and GP. I'm having a level process. Let us assume that for that this is the inflow rate, this is the outflow rate, Q in, this is Q out, level is here. If you want to get a input output model, give small step change here. For that, what is the change in H, get the dynamics, that model is called GP of S, input output model. Actually this is actual process, this is modeled as GP of S. Then again, this is the disturbance model. Suppose some disturbance is entering here. It may be change in density of the liquid, or it may be valve resistance changes either here or here. Like that, many disturbances may enter into here. Let us consider one disturbance, that is that increases the outflow rate means that decreases the outflow rate means you will get a model. If you suddenly a step decrease in outflow rate means definitely it will give a response like this. So you can model this as first order plus dead time. So that is called GDF. Yes. So this GD, this is the model for disturbance. This is model for input output. So this is design of feed-forward controller. What are the requirements to design a feed-forward controller? The first requirement is it requires the identification of all possible disturbances and their direct measurement. If you are not able to measure the disturbance, you cannot design a controller for that disturbance. So it's difficult to measure all the disturbance here. That's why it may not be possible to design a feed-forward controller for all processes. Any changes in the parameters of the process may affect the controller. The controller design may fail because of that parameter change. Deactivation of a catalyst with time, reduction of heat transfer coefficient due to fouling, etc. So if process parameters are changes, so if you consider here this example, here this CP is a process parameters. This is from the process parameters. Rho is the process parameter. Fi is actually, it is not process parameters. We are assuming that the Fi is keeping constant. Suppose this varies, the controller fails, because definitely this is multiplied by this. That's why this we are assuming that Fi is constant while designing that. If this changes, definitely the controller performance will degrade. Another thing is if rho changes, density changes, heat transfer coefficient, CP changes. If any changes happens in this parameter of this process, definitely the feed-forward controller fails. The performance may be degraded, but the feed-forward cannot be compensated by the. Another thing is, suppose these parameters are varying. Let us assume that these parameters are varying. In that case, these parameters are varying. Let us that these quantities are varying. That's why this controller itself introduces some disturbances, because this is not correct value. If these are all incorrect values at that time, then definitely it will. This also will introduce a disturbance. How to reject that disturbance? It is not. There is no way to reject the disturbance by this feed-forward controller. So that's why feed-forward controller cannot be used alone. It should be used along with the feedback controller. Similarly, it's not possible to measure the disturbance exactly. That is also there. In those cases, whatever the disturbances left out, that is not controlled by the feed-forward controller, all other disturbances should be managed by the feedback controller. That is the another reason why we have to use the feed-forward controller along with feedback. Feed-forward controller requires very good model for the process, which is not possible for many systems in chemical industry. So if you know the disturbance model and the input-output model, GD and GP, if it is very good, then only we can design feedback controller. These are the limitations of um, feed-forward controller. Now let us see the advantages and disadvantages. Advantages of feed-forward controller are, the one is it acts before effect of disturbance has been felt by the system. Already in the day before, yesterday we have seen that the need for feed-forward controller is reject the disturbance. Before it disturbs the process variable. We want to sense any disturbance is entering into that system. If we are able to measure that, we can take appropriate action before it damage the process variable. That is the first advantage. Second advantage, it is good for slow systems or with a significant dead time. For slow system, it is good. Because for fast system, the feedback controller itself take care of it. For slow system, suppose the system has a large dead time. let us assume that a jacket at a CSTR, in that very slow, its time constant is very large, say 5 minutes. So if any disturbance entered now, this will felt by this process after 5 minutes. The deviation in T will sensed here after 5 minutes. So after 5 minutes only it will take corrective action. Feedback controller will take corrective action. That takes another 5 minutes to change the effect here. Because of dynamics, it may take 3 times time constant of this process. So it takes long time to solve if the dead time is and the time constant is large. In that case, significant dead time is there. In that case, feed forward control will be very good. It does not introduce instability in the closed loops response. Does not introduce, it won't introduce instability, but it will not improve stability. Suppose the system has instability, the feedback controller will not mm, improve its stability, but it won't, the controller itself won't introduce any instability. That is the you should understand this point. This feed forward controller will not introduce any instability, but if the system has instability, it can't do anything. It can't do anything. Then what are the disadvantage of feed-forward controller? You see that it requires identification of all possible disturbance. You need the mathematical model GD of S to design the controller. Then that means you should identify the model and its parameters to design a feed-forward controller. Cannot cope up with the unmeasured disturbances. You do not know the disturbance, it won't take care. If already we have seen that the feed-forward controller will work only for the disturbance for which it is designed. So that is other unknown disturbances it will not take care. Sensitive to process parameters. Already we have seen this point in the CSTR example. This row CPR parameters. If that changes, definitely the performance of controller will change. It requires good knowledge of the process model. For all these above 3 points, you need the very good knowledge about the process. Then only you can design. But for an instrumentation engineer, if you know, give mathematical model, he will design. No need to know them. And of course, for safety aspect, we must know something about the process. Otherwise, we cannot be a safety engineer. But to design a feed-forward controller, we need a very good knowledge about the process. Then only it is possible to design the controller. Then it it does not require identification. What is the advantages of feedback controller? It does not require identification and measurement of any disturbance. Whatever may be the disturbance, the feedback controller will take care. That is the advantage. It is insensitive to modeling errors. Insensitive to modeling errors. If you didn't model that process, GP, you are not correctly modeled. To design a controller, you need a GP of S model. GP of S. This is not a process, this is model. You didn't model it correctly, but it works. Insensitive to the model errors, it will work. It is insensitive to parameter changes. So because you studied in electronics that when negative feedback is insensitive to parameter changes. The same thing here. It is a negative feedback controller. That's why it will suppress the changes, effect of changes due to parameter changes. So these are the advantages of um, feedback controller. What are the disadvantages of feedback controller? It waits until the effect of the disturbance has been felt by the system before control action is taken. So disturbance has to disturb the process, then only feedback controller will take action. It won't act in anticipate. If disturbance is entering, immediately it won't take action. It allows the disturbance to made an impact on the process variable. Based on that, it takes necessary action. That is one disadvantage. It is unnecessary for a slow process sorry, it is unsatisfactory. It is not satisfactory for slow process and a significant dead time. So the feedback controller is not good for slow process and a large dead time process. then it may create instability in the closed loop response. It may create instability. But here you see these two. If properly you design a feedback controller, it will improve stability. If the design is improper, it will introduce instability. The controller itself will introduce instability. On the other hand, whatever may be the design, feed-forward controller will not introduce any instability into the system. So that is a contradicting statement. Here, it introduce instability means you may get, you said one way you said stability, it improves stability. Yes, negative feedback will improve the stability, but the controller must be properly designed. How it introduces instability means if, for example, if the controller gain is large, it will be a threat to the stability for parameter changes. So anyhow, take this point as granted. It may introduce, not always. It may introduce instability in the process if poorly designed. So we have to use the feed-forward controller combined with the feedback controller. This is the feedback controller. This is the feedback controller. This part is a feed-forward controller. Disturbance is measured. Set point filter. Set point filter. Then this is the sensor to sense the disturbance. This is the feed-forward controller. This is filter, set point filter in the feed-forward controller. This is the feed-forward controller. So it gives its output. It should be added with the feedback controller output. So feedback controller output and the feed-forward control output both are added, and it is given to the final control element. This is the final control element. This is the feedback controller. This is the process. This is the measure sensor to measure the process variable. This is the process variable. Process variable. This is disturbance. Both are same. These two can be connected together. This is set point. It goes through set point filter. So set point is given here. Given here. That's all. Then ratio control. It is a special feed-forward controller. Ratio controller is a special feed-forward controller. Wild stream, controllable stream. Let us assume that the fuel flow rate is controlled. This is, suppose I am having a furnace here. The furnace here. This is the furnace for which the fuel is supplied here. For that, oxygen has to be supplied. That means the air has to be supplied to burn this fuel. So in this furnace, this is a wild stream because the fuel flow rate is not controlled by this process. This depends upon the demand. If more heat is required, the flow rate will increase. Demand reduces, this reduces. If any disturbance is coming to the process, this will either increase or decrease, depends upon the disturbance. So as far as this ratio controller is concerned, this is the wild stream. It will change, depends upon the requirement, or by some other controller will control this stream. Another one is controllable stream. So here we have to supply air to the process. This is fuel is supplied here. Fuel is supplied here. This is the furnace. This is the furnace. Depends upon the fuel quantity. Depends upon the fuel quantity. We have to supply air. That is the idea. So there must be a ratio, must be constant. Air fuel ratio must be constant. The desired ratio we know. If this is 1 time means here we need 5 times. Let us assume. So based on that ratio, we have to supply air. So what we can do, one type of design is measure the actual flow rate of the wild stream. Fuel flow rate is measured. Another one is here actual air flow rate is measured here. It should be equal to this ratio, desired ratio. That is set point. The set point is the desired ratio at which air should be supplied. Again, you are finding by dividing these two, you are finding again the ratio. The ratio is found. Actual ratio, it is we are finding. This is the desired ratio. If you find the difference between the two, that is the error. Based on that, this controller will regulate this valve. That is also a special type of feed-forward controller. In other words, ratio controller. The same can be designed in other way. Here, this air flow rate is directly given as process variable. The process variable, we are measuring the disturbance. We are thinking it as a feed-forward controller. Disturbance is measured, not process variable. Disturbance is measured here. This is the filter for set point. Let us assume that wild stream is there. If both are equal, this is equal to 1, this is equal to 1. But it is not so. That's why it is multiplied by desired ratio. This is 1 time means, this is 5 time means it should be multiplied by 5 or some other ratio that is required. So multiplied. This is a flow transmitter that measures the wild stream. It is given here. So if both are compared, depends upon the error, this feed-forward controller regulates the value. The same, it can be modeled like this also. Instead of finding desired ratio and actual ratio, we can do this way. That is also possible. Then, what are the applications of ratio control? Ratio control is used extensively in chemical process with the following the most commonly encountered examples. Keep the constant ratio between feed flow rate and steam in a reboiler of distillation. Feed flow rate and steam. If you want to maintain a constant ratio, then you can use that in a distillation column. In a distillation column of reboiler, to supply heat to the bottom liquid. For that, it maintains a ratio between feed flow rate and reboiler steam supply. Hold the reflex ratio in a distillation column. For that also we can use that ratio control. Control of ratio of two reactants entering the reactor at desired value. Ratio of two blended streams. Suppose you want to prepare a recipe, syrup, for that you have to blend two streams. How much this one, liquid A and liquid B are added together to prepare your recipe, say syrup, in that what ratio it must be A and B, like that. Hold the ratio of purge system to recycle the stream constant. Purge stream to the recycle stream constant. Keep the ratio of air fuel ratio. Already we have seen this. Maintain the ratio of liquid flow rate to vapor flow rate in absorber constant. Ratio of liquid flow rate to vapor flow rate. For that also we can use. Anyhow, all these are all to maintain some ratio in the flow rates. That is the whatever may be the process. We can use the ratio control. That's all about yesterday's syllabus. Now we have to start is there any questions, please? If you have any questions, I'm longing for questions. But no questions from you all. I don't know whether you understand or not. If you give feedback, then only I can understand that you are getting my point. Please raise your question. Say something.
Sir?
Are you
Hello?
hearing?
Yes, sir. Hello? Sir?
Hello?
Sir? Hello, sir. Sir, are you hearing me, sir?
Hello? Hello?
Hello, sir.
Yes, tell me.
Sir, while coming to ratio controller,
Hmm.
you explained that we get a ratio, right, sir, from wild stream and then controllable stream.
In that, what's your doubt?
Sir, which value is comes in numerator part and then which is come in denominator part, sir,
Okay.
while identifying a ratio?
Oh, okay, okay. Let's see. Introduce yourself,
Sir, my
please.
name is Valluvan, sir.
Oh, well done. Okay, okay. Thank you, thank you, thank you. Okay.
Okay, sir.
You are from Trichy.
Sir, Annamala University, research
Annamala, yes,
scholar,
yes.
sir.
But research scholar,
Exactly.
native
Yes, sir.
Trichy. Okay, okay, okay.
Yes, sir. Yes, sir.
1 minute, 1 minute. I will explain.
Okay, sir.
Okay. His question is how to find the ratio here, which is in the numerator, which is in the denominator, he is asking. Suppose we are assuming that this is 1 is to 5. 5 times air is required. Let us assume, I do not know the ratio. I am not chemical engineer. Please bear in mind. Let us assume that one time fuel fluid 5 times. So if you divide what you will get, if this is in numerator, if it is this is in numerator, suppose this is in denominator, means you will get 0.2, you will get 0.2. Suppose this is in the numerator and this is in the denominator, what you will get? You will get 5. Anyhow, if you consider the former one, you will get 0.2. Definitely, the desired ratio also will be in 0.2. So accordingly, you will get error. Suppose we divide this by this, means the ratio here is 5. If it is at steady state, this is 5, and this is also will be 5. So that's why it is simply mentioned as divider. So it is the choice of designer. They can divide either by FA by FB or FB by FA. Depends upon their assumption. Here also it will be changed. That's why no problem. Only thing is the controller gain will be depends upon the desired ratio. That will change. If we consider 5 means here the controller gain will be different. If it is 0.2 means controller gain will be different. That is the idea. No need to have consider now. At the time of design, we can decide either we have to divide FA by FB or FB by FA. Both are correct. Both are correct. Both way we can design. Are you getting?
Yes, sir. Yes, sir. I'm
Okay,
getting it.
okay, okay. Thank you. Any other question? Any other questions? Then, if no questions means we'll go to the next part. We have another 5 minutes. So let us start the next part tomorrow. Let us revise whatever we have seen today for another 5 minutes. Or shall I give introduction to the tomorrow's class? What do you want? Shall I revise? Please give your feedback. Shall I revise whatever we have seen today, or see the introduction to the next topic? Revise. Okay. CR says, sir, let us revise. Many are saying that revise. Okay, let us revise whatever we have seen today. Okay, thank you. Feed forward controller we have seen today. Feed forward controller can be designed for a disturbance that can be measured. If the disturbance gives a large deviation in the process variable, then we must design a feed forward controller. A measurable disturbance is required to design the controller, and we need the mathematical model for a disturbance model as well as input output model. Then we can design the controller. Here, this is the feed is entering into the heat exchanger. Two disturbances we are having. One is flow rate as a disturbance. Another one is inlet temperature. If both considered as disturbances, Then we can design one for flow rate, another one for inlet temperature. Accordingly, the coolant or steam temperature, if it is endothermic steam, if it is exothermic coolant, has to be manipulated. This is one example, one of the example as heat exchanger, feed forward controller in heat exchanger. Feed forward controller in distillation process. Already I said this is a reflux ratio control. It is to improve the quality of the final product. For example, if feed flow rate is increased, feed flow rate increased means that definitely suddenly there will be a sudden decrease in temperature. Then we have to increase the temperature immediately. Otherwise, the top product quality will degrade. So here, if you want to supply heat, here means it has to supply to the liquid, then it has to transfer here. It takes a long time. But in the feed forward controller, if any flow rate suddenly increases, means there will be a sudden decrease in temperature. How quickly we can increase the temperature? By reducing this reflux ratio. Reflux ratio is already I told, if any liquid flow rate is again fed back into the distillation column. Already we assumed that diesel and petrol. Diesel is in the liquid form, petrol is in the vapor form. Again, it is condensed. That petrol is again liquid. Petrol is again injected inside. Means immediately it will take the heat. So, but if you reduce that, definitely there will be increase in temperature. Constantly you are pumping some 5 liters per minute. Suddenly, if you decrease that, definitely there will be increase in temperature. If feed flow rate is increased suddenly, means if you want to increase suddenly the temperature, means you can reduce this reflux ratio. Another one is composition is measured here. If any change in composition, we have to increase the temperature or decrease the temperature, means based on the deviation the composition, we can regulate the steam supplied to that reboiler. Reboiler is injecting the temperature, injecting the temperature into the liquid. Temperature is required by this distillation column. It should be injected through this reboiler. That nominal steam is always go there. If any deviation is there, then that regulates this. Sorry, some vehicles are spraying disinfection. That's why they are making noise in the road. Then another example. Let us quickly see the design so that you can understand. This is the mathematical model of CSTR. This is for level and this is for temperature. In this case, the Fi equal to F at steady state. That's why Fi is constant. Another case is we are going to design a static model. That's why the dynamic part is 0. So we have to equate the equation for Q. We are designing a controller to make T equal to T set point. That's why instead of T, we have to substitute T set point. That's all. That will give you a feed forward controller. So that is implemented. That's why this filter constant is 1. But and we designed a controller for steady state. We didn't consider any dynamics. If we didn't consider the dynamics, definitely its performance will be poor. So we are going for dynamic feedback. In that case, this dynamic part is not made equal to 0. If we design the controller for that, the same assumption, T equal to T set point, and if you find the controller, this is the controller. The only difference is the tau s plus 1. That is the only difference. If you put that, the filter part become tau s plus 1. You see that both the servo responses, if it is dynamic controller, definitely there is a better improvement in the servo response. If you see disturbance, both one over the other, that's why it appears single. Both static and dynamic, I didn't mention in the previous presentation, both are identical. There is no difference in rejecting that load. But if you see the servo response, definitely this dynamic controller gives better response. So what's time now? It is 10:33 already. You have another seminar at 11 o'clock. That's why you must have some break. So let us stop here. Then this is general. Another quickly I will tell the design of this. Here, this is the expression from this expression. From this model. This is the process model. The disturbance is entering here, input output is entering here. So the y is equal to product of ms gp of s, d of s, gd of s. So this equation we got. Always feed forward controller is designed such a way that y is equal to y set point. That is pv equal to p set point. So we replace y of s y set point. We got the controller. So y set point is multiplied by some factor. This is the filter you have to introduce in the set point, and this is the actual feed forward controller is this. Feed forward controller is this. This is the general design procedure for feed forward. With this, let us stop here.